Hi, I am Ho Ki Chen. This work was done in the Hong Kong University of Science and Technology. In this work, we study the task of mass propagation, or sometimes called semi-supervised video object segmentation. Given the inputs at the first frame, including a fully annotated segmentation map, our algorithm predicts object masses for every subsequent Kiwi frame. The masses are temporarily propagated in an online fashion. One of the most popular approaches is space-time memory networks, STM, which utilize space-time meshing. First, we will look at its mechanism. Each object in the memory frame passes through the memory encoder once. A key and a value is generated as the output of the encoder. The same goes for the second object and the third. Then, the Kiwi is passed to the Kiwi encoder to generate a key tensor, which is matched with every object in the memory, and the corresponding affinity matrix is generated. Notice that we need to compute an affinity matrix for every object in the video. Lastly, the memory values are transferred to the Kiwi frame and object masses are decoded. We think this can be redesigned. Specifically, we should not need three affinity matrices to describe the feature transformation between two frames. We propose space-time correspondence networks, STCN. We first encode both the Kiwi frame and the memory frame with a key encoder, using only RGB inputs. Then, we construct the affinity using these two key tensors. Notice, we capture the correspondences with a single affinity matrix, and we have not looked at their object masses yet. This is the fundamental difference between STM and SCCM, and it makes our framework more data and compute efficient. With the affinity matrix, we only need a simple encoder-decoder structure to transfer masked features. We use the light network with some features we use from the key encoder. The final decoding stage generates all the masses. As the key features are generated from shared key encoders, the resultant affinity is more robust. We find that a more efficient memory scheduling can be used for SCCM. Namely, we no longer need the immediate last frame as a temporary memory. This mitigates drifting and makes SCCM much faster. Here are the quantitative results on the David's validation set. Our models perform the best and is the fastest. Next, we will take a closer look at the affinity matrix. It plays a core role in SCM and SCCM-like networks. However, not much attention has been given to the construction of the affinity matrix. Recall that it is a THW by HW matrix with each entry corresponds to the affinity between 2 points. We consider the affinity as voting. The memory nodes, collectively, vote for the outcome of every Kiwi node. From this perspective, we have some interesting observations. When the dot product affinity is used, a few memory nodes, labeled as triangles, will always have dominating votes over large regions, and many nodes will never have significant votes or contribution regardless of the Kiwi. This leads to a very poor utilization of the memory space. We propose using L2 similarity, which is negative squared Euclidean distance as shown at top right. With L2 similarity, our nodaloid diagram is formed on the right. Now every memory point can have a chance to contribute significantly to a Kiwi if the Kiwi feature matches that of the memory. This leads to much better use of the memory space. Here, we compare the performance of different similarity functions. Interestingly, we can further reduce the dimension of the key space and boost the performance when L2 similarity is used, but not when dot product is used. We think that this is because L2 similarity uses the space more efficiently and does not require as many dimensions. This, of course, makes the algorithm run faster and uses less memory. Our code and data are all open source. Visit our website to learn more.